50 years ago, the Apollo astronauts uncovered orange soil on the moon. The samples provided new insights into the development of the moon, but geologists expect that there was more to be told from these orange samples. In response to the task set out by EGB320, our team Slaves has developed a prototype lunar rover that can autonomously find and retrieve simulated samples in the laboratory environment. Our team developed the ROTBot, the Retrieval and Object Tipping Bot. The ROTBot was required to explore a 2x2 meter landing site with samples represented as orange golf balls. The robot starts on the lander and must explore the environment, uncover rocks, find samples and return them to the lander while avoiding obstacles with an aim of collecting 3 samples within 5 minutes.
Our robot was built upon 4 main subsystems: the mobility, sample collection, vision, and navigation systems. These were constructed hand in hand to ensure flawless integration. We designed the ROTBot to be modular in design. The 2-tier system was produced to ensure low cost and rapid development of all systems. All components were designed in CAD, 3D printed, and bolted together. The battery and caster wheels may be mounted in different orientations to optimize drive placement and to tune the center of gravity. For the electronics, a custom Raspberry Pi shield was designed to house the mobility, vision, and sample collection components. This was designed to minimize form factor and cost. The mobility system utilizes a front drive differential system in line with the vision axis for the ease of navigation and collection integration. This also comes with an added benefit where the ROTBot won't tip when traversing up and down the lander. Added treads and increased wheel thickness was designed to assist with traction.
The rod system was designed to tip rocks to uncover samples. The samples would then be scooped into the retrieval chamber, where it would be read by a proximity sensor. Once in the chamber, the sample would be enclosed as the rover traversed to the lander. When the rover reached the lander, the sample would be uncovered for its release. Good job, buddy! Onto the vision subsystem to identify objects on the lunar field, the Pi camera was flawlessly integrated onto the chassis using a slightly tilted L-mount. The camera would capture images in a HSV color space, which would pass them through the vision processing system to threshold and mask that captured image, segmenting based on hue, saturation, and value ranges for objects of interest in the image. The image would then be filtered by performing morphological erosion and dilation on each segmented object in the image, removing unwanted noise and false positives. Then be processed even further to identify the range and bearings of each object of interest relative to the robot, sorting and compiling the range and bearings for samples, rocks, obstacles, walls, and landers in a format usable for navigation. This process is repeated countless times for each image taken by the camera, generating a constant stream of range and bearings for navigation to read and act upon. Additionally, a proximity sensor was implemented to check whether or not a sample has been collected, and this information was sent to navigation.
The navigation system interfaces between the 3 other subsystems and controls the decision-making and path planning of the robot. The navigation state machine takes environment information from the vision system and determines the current state of the robot. It then sets the desired target velocities for the mobility system and triggers the sample collection when required. The ROTBot starts its exploration in the search state, where it spins until it sees a sample or a rock. It then navigates to the target location. When within range of an unflipped rock, it will enter the flip rock state. This was designed with fault tolerance in mind, ensuring that the robot will reattempt the rock flip if unsuccessful. Similarly, when within range of a sample, the robot will enter the sample collection state, where it will first align the sample and then trigger the collection sequence. With a successfully collected sample, the robot will search and navigate to the lander. When close to the lander, the robot will enter the lander alignment state, ensuring that the robot is able to drive up the lander successfully. Finally, when the lander hole is seen, the robot will attempt to release the sample. Artificial potential fields was used for the path planning and obstacle avoidance of the robot. Attractive potential fields are assigned to the samples and rocks, and repulsive potential fields are assigned to the obstacles. The integration of the 4 subsystems resulted in a successful robot prototype that is capable of avoiding obstacles, navigating to samples and rocks, uncovering rocks, collecting samples, and then returning them to the lander, all with a final budget of $165. Early testing demonstrated that our robot meets the requirements for a TRL3 prototype and is ready to progress to the next stage of development.
This video was sponsored by Listerine.